All right, so in this video, we're going to look a little bit at doing simulations. And I wanted to go through a little bit about how Excel, we can do simulations in Excel without having a lot of complicated machinery. There are definitely other ways to do simulations in Excel than the one I'm describing here, but I wanted to illustrate it with this particular strategy because it gives us a sort of a little bit more insight into what's going on behind the scenes. And then we're going to look at how Minitab can do these same simulations. Again, Excel can do them somewhat similar to the way Minitab can, but the Minitab graphs are a little nicer. So in Excel, we're going to do an example of a uniform distribution, basically involving a simulated die roll. So we've set up a ran between function in Excel that gives us outcomes that are values between 1 and 6. We can also use the rand function to give us a continuous distribution between 0 and 1, which is useful for coin flips, whether they're fair or not. But for our purposes, we're going to use the rand between function to roll outcomes of a single die. If in this case, if we wanted to roll 2 different die, then we could roll 2 simulated die using our ran between function and then add them together. So then we could see what the outcome of our pairs of die were. Traditionally, pairs of die take on what's called a triangular distribution, but that's not really relevant to our particular scenario right here, the shape of the distribution. But what we create then is we can create this, again, this sum. So again, think about, you're playing, a dice game that requires you to roll 2 die. What's your chance? Maybe it's craps or something like that. But what's your chance of getting some outcome that produces a 6, or some outcome that produces 11, or some outcome that produces snake eyes? So we can simulate this using our Excel function. And again, what I did was I created a column with toss 1 and toss 2, and I added them up, and that's our total outcome. Now there's more than one way to get a 6, right? So we get a 2 and 4 to get a 6, or we get a 1 and 5 to get a 6. But in our sum column, we're just looking at the outcome of the sum of the dies, not of the 2 dice, not what each individual one is producing. So in this example, I've done 10 simulated rolls, and you can see that I got a 10 and an 11 in one case. I got several 6s and 7s, which are actually the most likely outcomes, but I did get 1 snake eyes in my particular example. Now, if you're trying to generate this yourself using the same formulas, I didn't set a seed so that we would all get similar outcomes. Your answers will be different than my answers because it is pseudo-random, and it is starting at different places in the pseudo-random sequence. And so it is going to look more random because we are going to have different outcomes depending on where we are. But every time you hit there's a recalculate button in Excel, and every time you hit it, this will recalculate all of your values. And so you can see what the next 10 rolls would look like. Now, 10 simulations isn't really that many in order to determine sort of what are the likely outcomes. How, if we're trying to simulate the probabilities, we really need to do a lot more tosses than 10. Now, particularly for the pair of die outcomes, the most likely outcomes are sort of in the middle, and least likely outcomes are far away. We didn't even get all the possible outcomes. And with all of those different conceivable outcomes, we would actually want more tosses in order to have any idea at all about what the likely probabilities are. So we could extend, we can copy and paste our formulas, and we can get 1,000 tosses or 10,000 tosses. So technology is getting faster. Excel can do this a little bit more easily than it used to be. And again, I kind of want to stress, this is not the only way to do simulations in Excel, but in terms of us looking at sort of the mechanics, this is more about what Minitab is really doing, but behind the scenes when we get there. So what I did was I extended my 10 coin tosses, and I extended it to 2,000 tosses. And then I plotted my my outcomes in a histogram. Now, Excel's histograms are in my view, but basically each one of these bins represents a possible numerical outcome. So notice that this goes from 2 to 2.9999999. So this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the only integer outcome in this group is one outcome. Again, the bins are weird. You could probably simulate the outcomes with something like, or summarize them with something like pivot table or something like that. But what you get, again, is essentially what's called a triangle distribution. Basically, the middle 7 is the most common outcome, and then it works its way down, again, theoretically evenly on both sides. In real world, we don't get perfect evenness, but this is reasonably close to a nice triangle distribution. Now, if we want to use the RAND function again as a coin flip, then what we do is we set up the RAND function to generate a random number, and we test it to see if it's above or below a particular probability threshold. If our coin is fair, we set this up to be at 0.5, so both sides are equally likely. And then it outputs a 1 if the outcome is less than this, so true. Maybe we can call that a head. And then outputs a 0 if it's false. If it's in fact not less than 50, that's the tail. And then again, we can copy this down our column in order to get different outcomes. If we change this 0.5 to a different value, then that will set our head to have a different likelihood. So we could weight it in favor of heads, or we could disfavor it in favor of heads. Favor heads by increasing the probability of a head, increasing this p-value, or we could decrease the likelihood of head by decreasing this cutoff. So more heads, less heads. And again, the idea here is that in Excel, what you can do is you can just copy it down the column, and indeed copy it into many columns to look at many different attempts or trials. If you copy it down one column, this is our first run. And I did 20 tosses. So what is the outcome? What is the likelihood of getting head in an individual toss is 50%. But if you toss it 20 times, you're not always going to get exactly 10 heads. There's, again, this randomness, but you should get something close. And so the reason that I designated this H or 1 and 0 instead of H and T is so that I can easily add up the number of heads. And then I can copy this again into another column. And again, you can see that even before I did the screenshot, it recalculated everything. I can copy this into additional columns, and I can see additional examples of, well, what if I did the next 20 tosses? And what if I did another 20 tosses? And again, sometimes you get really close to 10. Sometimes you get even exactly 10. Sometimes it's higher than 10. Sometimes it's lower than 10. There's a little bit of variability, but usually you're going to stay around, whatever that means, around the 10 range, because 10 is half of 20. But again, the randomness means it's not always going to be that way. So what we're simulating in this example is a binomial probability distribution. We're essentially saying what is the probability of getting exactly a 10 or exactly a 9 in a given in a given set of 20 tosses. And again, we can simulate what that looks like. We can calculate all these sums. How many heads did we get when we tried this 20 tosses? And what if we tried it again? And in fact, I did it 200 times, the 200 of these columns of 20 coin tosses each. And then we can make, again, we can make a distribution of it in order to see how that distribution behaves. And so what we end up with in this example is, again, I've tried to separate this so that the histogram is not doing too many weird things. In this particular example, a couple of these, some of these bars have only one value in them. Some of the ones down on the end may have 2 values in them. This has both 15 and 16 in it. But most of these histogram bars have only a single value in it. And the center of the distribution you can see is right around 10. We do have a little, in our 200 examples, we have a little bit more 9, a little bit more 11 than we have 10. But again, that's just random. There's no reason that that particularly should happen. If you were to rerun this 200 simulations again, again, you would expect to have something that looks more, not with these 2 high bars around a lower one, but sort of more symmetric, more normally looking. But again, it doesn't look too bad, other than the fact that we didn't get that many exact 10s. Now, if you change the probability of success from 50%, which is a fair coin, to something that is lower, so maybe 20% chance of success, then what you get is you get fewer outcomes. You don't get as many heads. And so you're more likely to get 0 or 1 or 1 and 2 or 2 and 3, much lower outcomes. You're not really likely to get 10 outcomes. The peak is going to be around 2, well, 2 to 4 outcomes in a set of 20% probability. If you're doing 20 tosses, 20% of 40 of 20 is 4. And so that's where you would expect the peak to be. And so this is somewhat consistent with that. If we set the probability higher so that there's more likelihood of getting heads, like 80%, then what you get is you get a shift in the other direction. You get more outcomes. Likely to be 80% of 20 tosses would be about 16. So you'll get a peak around 16. And then again, you'll have, instead of we saw in the previous example, this was more of a right skewed distribution rather than a symmetric one. In the case of 80%, what we get is a left skewed distribution because it's all bunched up here against 20, which is, you can't get more than 20 heads when you flip the coin 20 times. There's no place to go, but you'll get a sort of a left tail instead of a symmetric distribution. And again, if you're trying to replicate this, your histograms are not going to look exactly like mine because it is random, but they should have the same general shape. Symmetric approximately when you're around 50%, right skewed when you're around 20%, and left skewed when you're around 80%. And again, if you also include more examples, I only did 200 of these sets of 20 for this illustration, but if you do more of them, if you do 2,000 of them or something like that, you calculate them and you collect the outcomes, let's say 10 more times, then what you should get is something that looks much cleaner, because more data tends to produce, again, tends toward the sort of theoretical outcome, according to the law of large numbers. Now, both in Excel, if you use the simulation techniques. There's also a data table method where you can do simulations very quickly and not sort of have to deal with all of this, sort of individual formulaic machinery. There are ways to do this in Excel, but what we're going to do is we're going to switch over to Minitab, because what we want to look at is how, this Excel component, I tend to think of it as it's very simple and straightforward. It doesn't require a lot of mechanics in order to get this to work. And you can kind of see what's going on in the background. In Minitab, we can actually sort of bury some of this in the background, and we can just run more trials to see better outcomes. So I was just mentioning that, like, I only did 200 of these binomial experiments. What if I wanted to do 2,000 or 20,000? So that would make that sort of machinery as easy as it is. It would still make it somewhat cumbersome. In Minitab, we can actually just do it all behind the scenes and just report the outcomes. And it's, again, a little bit easier and sort of more directly built into the system. Some of the ways that you have to do this in Excel are less accessible because you need to know how to do more things, or they're sort of non-standard and you have to install, like the data analysis tool pack and things like that. But Minitab was designed for this. So if we go to Minitab, look for the menu that is called Calc. And then from that menu, you want to look for random data. And then from within that submenu, select binomial, because again, we're simulating those coin tosses we were just looking at. Now, you can also simulate other kinds of variables. There's our triangular distribution that we were looking at earlier. There's lots of sort of standard distributions built in here. The most common ones are at the top, and then sort of the less common but still included ones are closer to the bottom. But we're going to just use the binomial one for this particular illustration. And so if you click on that, what you get is a pop-up box. And what we're going to do is, again, we're just going to sample what we were just looking at. We're going to run 200 rows of data. We're going to store the data in column 1 in our worksheet. The number of trials we're going to run, again, we're just going to replicate what we were just doing in Excel. Number of trials is 20. Event probability is 50%. So that's the probability of our success. We'll pretend that heads are success. And then if you hit OK, the outcomes are spilled into the column C1, and then we can make a nice histogram of our fair coin results. And again, you can see this is somewhat similar to our distribution that we had earlier from Excel. This center 10 value is in fact the peak in this particular simulation. We see a little bit of wiggle, on the end here, but otherwise this does look, again, centered around 10. It's not really symmetric. We have some, excess here and not quite as many here, but again, it's only 200 simulations. You'd expect a little bit more lumpiness with 200 than with 2,000 or 20,000 or what have you. Now, we can then redo this. If we change the success level to 0.2, we'll dump that into column 2, and then change the success level to 0.8 and dump that into column 3. So using exactly the same steps that we did before. Here's our 0.2 distribution. Again, you can see it's a little bit, it doesn't look too asymmetric here, but it is a little bit left skewed. And then our 0.8, again, it's a little bit right skewed, or sorry, in this one, it is a little bit right skewed. This one is right skewed. And this one is a little bit left skewed. But still, it looks a little bit nicer than what we got in Excel. But again, this is simply random. There's a lot of variability with only 200 samples. Now, we can combine them. We can make the nice thing about Minitab is you can make a nice comparison of your histograms all on the same graph, which is one of the nice things about histogram, about Minitab, is that it does do graphs more nicely, I think, than Excel does, especially these statistical graphs. Here, I've taken my fair coin versus my 0.2 probability, my 0.8 probability from the previous 3 separate graphs. I've now made one graph and plotted them all at the same time. And so we can see in the center, that's our fair coin. This is our very unfair coin with 20. And this is our very unfair coin with 80% heads. We have a nice legend here. Now, if I wanted to see more skew and more separation, I can change my probabilities. My left skewed one to 0.1 and my right skewed one to 0.1 and my left skewed one to 0.9. And so again, we can then output these to new columns in Minitab. Each one of these runs separately from our random number generator. And then we can see that this is our 0.1 distribution. Again, you've got a real tight peak here. And then with 20 tosses, you would expect the most likely outcome to be about 2. And then, you have a bit of a tail toward the right. Here's our 0.9. Again, we would expect 18 tosses to be our most frequent. And then you have a little bit of a tail because it can't get higher than 20, right? It can't get lower than 0. So you have a little bit of a left tail. And then in the center, you have your nice symmetric 0.5 run. Now, what I've been doing is I've been using this mean of the binomial distribution, sort of estimate where I'm expecting my means to be. For the binomial distribution, remember the mean is equal to NP. So that's how I know that like 10 should be at the center here and 18 should be at the center here and 2 should be at the center here because 20 times 0.1 is 2 and 20 times 0.9 is 18 and 20 times 10 is, or 20 times 0.5 is 10. So that's all just generated from that. And then again, if you are interested in going further and like simulating this with a normal distribution, you would need the standard deviation. And the standard deviation for the binomial distribution is NPQ under the square root, because NPQ is the variance. And again, you can do additional simulations. You can increase the number of trials. Again, in Minitab, that's super easy to do. In Excel, what I would suggest is set up your like 200 trials. If you wanted 2,000, just recalculate. But every time you calculate it, copy and paste the outcomes into plain text into another row of your table. And then just do that however many times until you accumulate the required number of simulations. So if you have a simulation set up for, say, 200 sets of 20 coin tosses, but you want to increase it to 2,000, copy and paste your values from your 200 simulation 10 times, and that'll create your 2,000 simulations. Because remember, every time you hit enter, everything's going to recalculate. So every time you paste the values from one set of outcome, it will store those values, but then it will recalculate everything else. And so when you paste again, it'll record the new outcomes, and then it will regenerate another set and so on. But as I said, there are other ways to do this, but this is essentially how these work. Again, the idea here is to explore what the distributions are doing. What are we trying to model when we talk about a binomial distribution or a normal distribution? When we do simulations with them, we're trying to, I guess, sort of understand what's going on. So it's harder to go out into the real world and do this many times in order to get this conceptual understanding. But being able to explore some of these distributions with numerical simulations gives us a sort of a better conceptual feel without having to sort of take the time consuming work of going out and looking at something in the real world that does this. We can get that deeper understanding through technology.